Okay, everyone. There's no one here, but it is 5:30, so I've got to go ahead and get started. I want to start off by letting you all know that tomorrow at 8 a.m., that's normally when I do one of our labs every Tuesday and Thursday at 8 a.m. Tomorrow I'm running some family members to the hospital, so I won't be able to do that tomorrow. Hopefully, I'll be able to do it in the afternoon, or I might be able to do it tonight. I'm not sure yet, but you'll see it when it's posted on my YouTube channel. So, again, I highly recommend you subscribe to my YouTube channel, even if you just do it for the semester. That'd be great because every time I post something there, you'll get an email, or you can set it up so that you'll get an email every time I post something, and you should be able to tell from the title whether it's for your class or another. So, I highly recommend that. The video introducing tomorrow's lab will be posted sometime tomorrow on my YouTube channel, and you can watch out for it there. But like I said, I will not be there at 8 a.m. So. Now, last time we spoke, we were working on friction, and I had already explained the difference between static friction and kinetic friction. So now we're going to start working some examples with that, and then we'll go into rotational motion. And once we do that, then we'll move on to basically there's a single problem we can work where we're going to take into account air drag or the force of drag, which is the drag force or the resistance due to air. So we'll start off with example 5.3. Oops, I just noticed I don't think I actually duplicated that, so let me do that real quick. So as I said, we are starting off with example 5.3. So that says pulling against friction. A 10 kilogram box is being pulled along a horizontal surface by a force FP equals 40.0 newtons applied at 30.0 degrees angle above horizontal. This is like example 411, except now there is friction, and we assume a coefficient of friction of kinetic friction of 0.30. Calculate the acceleration. So let me go ahead and start off with that. As I said, this is example 5. Your book uses dashes. I'm using periods. It doesn't really matter. But I want to write down the information we were given. So the information we were given was that the box has a mass of 10.0 kilograms. The pulling force FP is equal to 40.0 newtons. And the angle theta above the horizontal at which that FP is pulled is 30.0 degrees, and the coefficient of kinetic friction mu sub k is equal to 0.30. So with that in mind, let me go ahead and draw the picture, and what we're asked to calculate is the acceleration a equals question mark. So I'm going to draw the picture. Basically what we have is a box with a mass of 10.0 kilograms sitting on a friction full surface. So that's just a surface, of course, that has friction, something like that. And of course, we have other forces acting on it. We know, for instance, one of them, notice I drew it blue because it's not parallel to either axis. So I'm just drawing it some color other than red or green.
Hey,
And that
Professor.
angle, yes, is there. Oh, I haven't
You,
given you the screen yet, have I? Thank you for speaking up on that one. I was just running along, having a good old time. All right, so
thank you.
yeah, appreciate it. Got to be terrible if I was drinking before I came to class. If I can't remember this is pretty bad. All right. Well, at least I can blame it this time that I was doing like 12 different things at once. I was trying to get rid of my dogs. My dogs just started barking. My mom was just coming in. And I was also trying to create a duplicate file here. So, all right, that's the document that I have. Let me read the question again to you guys. Example 5.3, pulling against friction. Can we put them in the room? Sorry. Pulling against friction. A 10.0 kilogram box is being pulled along a horizontal surface by a force FP equals 40.0 newtons applied at a 30.0 degree angle above horizontal. This is like example 411, except now there is friction, and we assume a coefficient of kinetic friction of 0.30, and they asked us to calculate the acceleration. So that's just the diagram right there. And again, part of this that we're learning in chapter 4 and 5 is really about free body diagrams. So that's a major part. So let me go ahead and draw our free body diagram. The free body diagram we'll have our x-axis positive pointing to the right. It's got our y-axis positive pointing upward. I have a mass, which, as I said, until we talk about torque and center of mass and stuff like that, we have to sort of assume everything's acting like a point particle. So this mass of 10 kilograms is really a point particle of mass 10 kilograms. We do have acting on it a force in the negative y direction, and that's the weird force. That's the one force that's being caused by something that's not touching it. Remember, all the forces on a free body diagrams, if you want to check your free body diagram to make sure you've included all the forces, you have to just take into account everything touching it. And then if you've accounted for everything touching the object, then the only thing you have left is the gravitational force, which is what we call weight. And of course, that's not touching it because you don't necessarily have to have the object touching the earth in order to be pulled by the gravity of the earth. So the other objects that are touching this box, of course, are the floor. And that floor is, of course, creating a vertical normal force in the positive y direction. So that's what this force is right here, and that's F normal. We also have that pulling force, which was I said was at 30 degrees. So that pulling force is 40.0 newtons at 30.0 degrees, like that. And then, of course, if we're pulling it that way, that means it should be moving horizontally to the left, I mean to the right, and that means the friction force should be acting to the left, and that is a negative direction. So I'm going to draw that vector in red. And then, of course, I just use the script F like we do for our function. Now, before we can go on, we also have to break that blue vector up into components that are parallel to the x and y axes. In other words, we have to break it down into its constituent x and y components. We can see that if we try to travel from the tail to the head along the axes, we're either going to have to go first up the vertical axis and then to the right along the x-axis, or if we chose to do it the other way, we'd get the same answer. We would go to the right along the horizontal axis and up along the vertical axis. So again, that's the method you do use to figure out whether the individual component will be positive or negative, and it doesn't matter whether you go x first and then y, or y first and then x. That's just me showing you that. So we did discover that the x component would be positive, so I'm going to draw that in green, and it's right here. So this is the x component of force, so I'll call this Fp sub x. And then the y component of force is also in the positive direction, so I'll draw that green as well, and that's Fp sub y. So now, just before we take our training wheels off, we want to try to consider the individual trig functions. So the sine of theta, which is actually the sine of 30 degrees, is equal to opposite over hypotenuse. Remember, when you draw the right angle, that arrow or that right angle looks like an arrowhead pointing to the hypotenuse. So that tells us this is the hypotenuse. The adjacent angle is the one touching, or the adjacent side is the one touching the angle. So that means this side right here is the adjacent, and that means this is the opposite. With that in mind, we can go ahead and say sine of 30 degrees is opposite over hypotenuse. So that is F Py over 40.0 newtons, and therefore Fpy is positive 40.0 newtons times the sine of 30.0 degrees. And of course, the sine of 30 is 1/2, so that gives us 20.00 newtons positive. Notice I did carry an extra digit, as we should. Now I'm going to write out what the cosine of 30.0 degrees is. Cosine is equal to adjacent over hypotenuse. As I said, the adjacent is the side touching the angle. So that's going to be Fp sub x over 40.0 newtons. Therefore, Fp sub x is equal to positive 40.0 newtons times the cosine of 30.0 degrees, which is root 3 over 2, or 0.866. And you're welcome for the entertainment with my dogs. I'm sure you're all really helped by that. So 40 times the cosine of 30 gives me 34.64. And again, that would be positive. So 34.64 newtons is the x component. Now all we have to do, and this is the same process over and over again. So this is like the first one for your class that we're doing with friction. So you got to learn the technique. And basically the first technique is you've got to do the summation of forces in the y direction equals mass times acceleration in the y direction, i.e. Newton's second law. And when you do that, you've got to do that to determine normally the normal force. And then you do the x component, summation of forces in the x direction equals mass times acceleration in the x direction. You've got to do that one to determine the actual acceleration of the motion of the object. So if I start off with the summation of the forces in the y direction equals mass times acceleration in the y direction, what you got to realize is the box will be pulled horizontally like this. So it'll just be moving across like that. And therefore, the actual y coordinate of the box, which we set at 0 because we put it at the origin, that y coordinate is not going to change at all. And since it doesn't change, that means the velocity in the y direction is 0. And since the velocity in the y direction is 0, and then you wait a couple seconds and it's still 0, and you wait a couple seconds and it's still 0, that means the acceleration in the y direction is 0. So we're going to make that argument several times. I'm probably not going to do all that work to explain it all to you every time, so make sure you commit it to memory now and understand. So now that we have that, we can now say the summation forces in the y direction is equal to 0, and those forces are the normal force, which is positive, so I wrote that as positive Fn. And remember, the left-hand side is adding forces, but when the component is negative, you'd say plus or minus. So why write two symbols when you can only write when you can get away with just writing one? This is the other force acting in the negative direction, and that's the mg, or the weight. And that, of course, is 10 times 9.8, which would be 98.0 newtons. So it's Fn minus 98.00 newtons. And now, in addition to that, we have this component of force right here, a y component of the F sub p, and that's acting in the same way as the normal force. So that actually relieves the normal force, or the surface, from having to do quite as much, or have to put up so much force. So in this case, we're just going to write it as plus, oops, better get my blue back on, plus Fp sub y, and we already determined that Fp sub y was 20.00 newtons. All that equals 0, and we can solve therefore for the normal force, and we get the normal force is equal to 98.00 newtons minus 20.00 newtons, which equals 78.00 newtons. So that's what our normal force is. Now, in addition to needing Newton's second law, we also need, of course, the friction force. And the equations we use for friction force are, and I really should have wrote this book to begin with, but I got sort of sidetracked, so I'll write it up here. Solution. What we needed was the summation of the forces is equal to mass times acceleration. That's Newton's second law. We also need the kinetic friction force is equal to mu kinetic times F normal. And that's pretty much it. So now we can go on and write the summation of forces in the x direction. Summation forces in the x direction equals mass times acceleration in the x direction. Now that's the only acceleration we're really going to be dealing with, so I'm not going to subscript it x. I'll just leave it a. But again, how do we go about doing that? All I got to do is write all this information in and then solve for it. I realize I'm not looking at your chat. Y'all can go ahead and chat me your first and last name. That would be helpful if you haven't done so already. But actually, it looks like nobody did. So just reminding you. All right, now we've got summation of forces in the x direction equals mass times acceleration in the x direction. If you look at the free body diagram, and this is the whole purpose of the free body diagram, is so that you can fill out Newton's second law without missing anything. In this case, what we're going to have is a f p sub x in the x direction pointing positively. So that's going to be, in fact, 34.64 newtons. That's the f p sub x. And then acting in the negative direction would be mu kinetic times the normal force. Well, we already know mu kinetic is 0.30. And I'm going to go ahead and say that's 3 sig figs just because it makes the dealing with sig figs a little easier, even though the likelihood of finding the coefficient of friction to 3 sig figs is really pretty rare. But anyways, now I'm going to take that, of course, and multiply it by the normal force, and we already found that the normal force was 78.00 newtons. So I'll just write under this just to remind you what this is. This is mu kinetic times the normal force. And that's really the only two forces acting in the x direction. So we set them equal to the right-hand side of Newton's second law, which is mass times acceleration. The object's mass is 10.00 kilogram. Notice I'm showing an extra sig fig again. And all of that is times A, which again, as I suggested, I would not be subscripting that. So if I take the 34.64 and I subtract from that point 0.3 minus answer minus zero point 0.3 times 78, that's going to give me 11.24. So I get 11.24 newtons. That's the answer when I subtract 34.64 minus zero point 0.3 times 78. So I get 11.24 is equal to 10.0 kilograms times A. I left off the extra sig fig there, but we can see immediately that A is just going to be 1.124, and that's newtons divided by kilograms. And of course, a newton is a kilogram meter per second squared. So if you divide that by a kilogram, you're just going to get a meter per second per second. So that's our acceleration, and that's of course with an extra digit, but that's it. Anybody have any questions on that one? Okay. Now, the way your book did it, they were using basically 3 sig figs, except for the coefficient of kinetic friction, and that had 2 sig figs. So there is a possibility that it might have only limited you to 2 sig figs, and that's why they gave you 2 sig figs. I didn't follow that out. I just kept my 3 sig figs, and hopefully everybody can follow that. So it looks like no one has any questions. That's good. We're going to move on to example 5.4. And this is a big conceptual example, and it's very important. Not only that, it's something that you've probably experienced yourself if you've done any kind of moving around of stuff. For instance, I used to work at Home Depot, and sometimes we'd have dishwashers or table saws or stuff like that, big boxes that you'd have to slide around on the concrete. Sorry, trying to get my dog to be quiet. So, what you might have noticed is if you ever try to push like a really heavy box, like a refrigerator or something like that on a surface, even though you've been inside a Lowe's and Home Depot, their concrete's usually pretty smooth, but it's still kind of hard to do it. Well, what's going on there is when you go to push it, if it's really, really hard to push, you'll find your body naturally moving so that your arms are horizontal and that you're pushing like this. And that's your body basically figuring out that, oh, wow, I need to supply every bit of my force to act in exactly the direction I want to move this box. If I, push down on it or up on it, I'm stealing some of that ability to force. But not only that, if you did it, you'd also discover that if you push down on it, you're actually making it harder on yourself. This example is hopefully going to show that. They specifically say, conceptual example 5.4, to push or to pull a sled. Your little sister wants a ride on her sled. If you are on flat snow, will you exert less force if you push her or pull her? See figures 5, 6a, and b. Assume the same angle theta in each case. So with that one, let me draw you a little bit of a picture, even though I usually don't write too much with conceptual examples. In this case, I will. So this is example 5.4. And in this case, we're going to have a small child on a sled like this, and you've got two choices, either the father pushing FP at this angle theta, or we have again the same scenario like this. And in this case, we're going to imagine that instead of pushing on his shoulders, maybe he's got like a rope tied to the front of the sled, and then up at that same angle theta is that same force FP, say. Okay, and this is supposed to be the exact same angle. Clearly, I didn't draw it that well to be the same angle, and of course, my OCD is not going to let that stay, so I had to change it. So, anyways, uh, trying to make it roughly the same force there. So that looks a little better. That's theta. Now, what we just learned from this last example was that this component in the upward direction allowed our normal force to be smaller because I ended up getting 98 minus the 20, and the 20 is the y component. So when you have a force that's pulling and in the upward direction, then you have a x component that is positive and you have a y component that's positive. That positive y component is doing a little bit of the work that the normal force would otherwise do. So you're actually decreasing the normal force by pulling up on it like this. However, in the case of us pushing, then the components are to the right, which we have to have, but the y component is in the downward direction. Because that y component is in downward direction, we would have Fn minus 98, and then we'd have minus 20.00 newtons, so that instead of 78, we'd actually have 118 newtons. So you can see that when you pull an object with a slight upward angle and you push this object with the same downward angle, it turns out that the downward angle is going to make your normal force larger, and therefore your friction force will be larger, and therefore you'll need a larger force to push or pull it. So pushing is requires a larger force than pulling, unless you make a really big effort to make sure you push perfectly horizontally instead of downward at all. Any questions on that? All right. So we're now going to go back to hopefully that video that I asked you guys to watch. I sent it to you via announcement and via email just to remind you to watch the video that was finishing up the examples of chapter 4. And I did an Atwood machine, I did a fuzzy dice, stuff like that. So that's some of the stuff we need to do. The good news is, whether you watch that or not, I'm getting ready to do the same sort of problem. I'm doing an Atwood-like machine, except this time it's an Atwood machine where instead of both objects hanging vertically, one is sitting on a horizontal surface and the other one's hanging vertically. So that brings us to example 5.5. So let's see. Example 5.5. It says two boxes and a pulley. In figure 5.7a, two boxes are connected by a cord running over a pulley. The coefficient of kinetic friction between box A and the table is 0.20. We ignore the mass of the cord and pulley and any friction in the pulley, which means we can assume that a force applied to one end of the cord will have the same magnitude at the other end. We wish to find the acceleration of the system A, which will have the same magnitude for both boxes, assuming the cord doesn't stretch. As box B moves down, box A moves right. So they're giving you a lot of stuff there, and some of those sentences probably seem irrelevant to you, but they really are relevant. So I'm going to try to walk you through this. I'm going to first write down what we were given. We were given, for instance, that M sub A is equal to 5.00 kilograms. Notice I'm adding an extra digit, and M sub B is equal to 2.00 kilogram. Again, I'm adding an extra sig fig just because I like working with three sig figs instead of two. The coefficient of kinetic friction between box A and the table is 0.20, so that's mu sub k for kinetic is 0.200. Again, I added an extra digit. And what they want to know is the acceleration equals question mark. Now let me draw the figure and then I'll draw a free body diagram. So the figure is basically a tabletop, something like that. And then mounted on the tabletop is a pulley. And then on top of that tabletop is the 5.00 kilogram box. And the rope is tied over, or the rope or string is tied over the pulley. And then the pulley, of course, and this could be a really big table, but I should probably shorten the rope to make it not look so big. Uh, but anyways, now I'll hang another box from here, and this is the 2.00 kilogram box. So that's that box right there. So now we have the two boxes and the table and everything drawn. Now I need to draw free body diagrams, and this is what I was trying to stress to you guys in that other video, hopefully that you watched. But when you have two bodies or three bodies, like I did with the chain of boxes in that video, it's usually best to at least draw a free body diagram for each of the independent bodies, and then you might even need to or want to draw one free body diagram for the whole system as if it's one object. It seems a little confusing to try to do it for an Atwood type machine because the two objects are separated by a string and that string's massless and it just seems weird. So I never recommend people do that for an Atwood type machine, but like for a string of boxes, that can be very helpful. So let's draw our free body diagram and let me explain some things. So first off, if you think about pulling down on the 2 kilogram mass here on the right, so I'm pulling down on that. If I pull down on that, then this tension in this rope, the force that I'm actually applying to the rope, is got to be big enough to rotate this pulley, which could have a lot of mass, and to overcome the friction of this pulley, which could be a large force as well. And it's got to pull that rope and it's got to pull that 5 kilogram box against friction. Okay, so if the pulley is actually massive and has frictions, then you can clearly see that the tension on the right between the pulley and the 2 kilogram mass has got to be larger than the friction on the, or excuse me, than the tension on the left. The reason why is because once you get to the left hand side of the pulley, the only job that rope has to do is to pull the 5 kilogram box against the friction, whereas the string over top of the 2 kilogram mass had to pull that box against friction, so it's already equal to the same tension that one had, but it's also got to provide enough force to rotate a pulley that has mass and to rotate a pulley that has friction. So clearly the tension in the right hand side of the string would be larger than the tension in the left hand side of the string. But that's why the author said we ignore the mass of the cord and pulley and any friction in the pulley, which means we can assume that a force applied to one end of the cord will have the same magnitude at the other end. So that's him explaining all that stuff that I just did. It might not have been a sufficient explanation. That's why I explained it to you with a counter example. So hopefully that helps. Now I'm going to draw the free body diagrams. And when I do that, I'm going to tell you something else about why they said as box B moves down, box A moves to the right. So first off, I'm going to start with my free body diagram for the 5 kilogram mass. And what I'm going to do is treat the direction that I expect it's going to move to the right. In other words, I'm going to treat that as the positive x-axis. Therefore, I have here a mass of 5.00 kilograms. And now what forces do I have acting on it? Well, the things that are touching it are the tabletop. Therefore, I have a normal force, F normal, which points in the positive vertical direction, the positive y direction. So that's F normal, and hence I drew it green. We also have the tension in the cord, or the actual string that's touching it, and that pulls it in the positive y direction, or excuse me, the positive x direction. And I just call that T. Your book calls it F sub T. But again, it's pointing to the right, so that's a positive direction, so I drew it as green. And we assume, just like the drawing has, that the pulley is just the right height so that the string is not giving an upward component or a downward component of force to the 5 kilogram box. Now, that's all the things that are touching the 5 kilogram box. So we're left with the one thing that doesn't have to touch it to apply a force, and that's the force of gravity. And therefore, the weight of this object is right here. W equals mg. And of course, that's 5 kilograms times 9.8, which equals 49.0 newtons. Now, 9.8 times 10 obviously is 98, and 5 is half of 10. So when I multiply 5 times 9.8, I should get half of 98, which is 49. That's where that came from. So that's my free body diagram. Now, as your book also mentioned about the pulley not getting slack, or excuse me, not stretching, the string not stretching or anything like that, I'm going to go a little bit further, and I'm going to say, one, we're not considering cases where the string actually has slack in it. Okay, and two, we're also not considering cases where the string is stretched. Because of that, we have something neat that happens. If I pull this 2 kilogram, or let's say, if I pull this 5 kilogram mass to the right 1 inch, then because the string's not going to get slack and the string's not going to stretch, then the 2 kilogram mass is going to move down 1 inch. That tells us that the displacement, in some sense, for the mass A is the same as the displacement for mass B. Now, if I up it a little bit more and consider, what if I move the 5 kilogram mass to the right 1 inch in 1 second, then what that means is the 2 kilogram mass is going to move down 1 inch in 1 second. Excuse me. The 2 kilogram mass is going to move down 1 inch in 1 second. So that tells us that the velocity of the m sub a, the 5 kilograms, is equal to the velocity of m sub b, the 2 kilograms. Now I'll step it up one more level. If I move the box 1 inch to the right, the 5 kilogram box 1 inch to the right in 1 second, and then 2 inches additionally in the second, then what I notice is the 2 kilogram box is going to move down 1 inch in the first second and 2 inches in the second. So that tells us that the two accelerations are the same. As long as, notice I kept telling you, when the 5 kilogram box moves to the right, the 2 kilogram box moves down. So that tells us to keep from having to have yet another equation to relate the acceleration of the 5 kilogram mass to the acceleration of the 2 kilogram mass. I have to actually try to set up the coordinates so that whatever happens with the 5 kilogram, like it moves to the right in the positive x direction, if I set up the 2 kilogram mass to have a positive x direction pointing down, then I won't have to make a separate equation to relate the two accelerations. So all of that means that my free body diagram for my 2 kilogram mass is going to show an x-axis pointing down. It's also going to show the 2 kilogram mass, of course, right here. So the 2 kilogram mass is the hanging mass, and of course we have acting on it. Since down is the positive direction, we're going to say the force of gravity, the weight W, is equal to 19.60 newtons. And actually, my 6 got a little narrow there. I'm not happy with it. So 19.60 newtons is the weight. And then if you were actually in that 2 kilogram mass, you'd probably think, oh, well, thank goodness that rope back there is behind me because it's keeping me from falling at G. I might have gotten hurt. So that tells you that the tension in the string for the 2 kilogram mass is actually pointing upward. and therefore that's the tension. And remember, since the pulley is massless and since there's no friction in the pulley, the tension on the 2 kilogram mass is the same as the tension on the 5 kilogram mass. Not only that, notice how they appear to cancel one another out. That is the norm. So when you break up a system so that you have two free body diagrams, if the two free body diagrams have the same tension in it on one side and the on one diagram and the other, then you expect those two diagrams to have the tension pointing in two different directions. Now, if you don't understand that right now, that's okay. It's going to take you a little while for it to make sense, and some of it just comes from experience that you consistently get the right answer. But just remember it, memorize it, know that's what it's got to be, and use that repeatedly because all this stuff I'm doing is stuff you're expected to be able to do. All right. Now I can go ahead and use my summation of the forces in the y direction equals mass times acceleration in the y direction to figure out the normal force, but I'm going to start off with solution. And what we know is we're going to use the summation of forces in the y direction equals mass times acceleration in the y direction. We're going to use the summation of the forces in the x direction equals mass times acceleration in the x direction. We're going to use the kinetic friction F sub k is equal to mu k times F normal. And that's pretty much it. The big trick here is we're going to have a system of equations and we've got to deal with that. And I'm going to show you a way, which I've already shown you in that other video, but this one will be another instance. Yeah. So for the 5 kilogram mass, I'm going to go ahead and write the summation of the forces in the y direction equals mass times acceleration in the y direction. Now, this 5 kilogram box, just like the previous box, is going to be moving perfectly horizontally. That means the y coordinate, which is 0, is not going to change. So the y coordinate not changing between two particular times means the y final minus y initial is 0 minus 0. And then divide it by any amount of time, you're still going to get 0, so the velocity is 0. But if you try two other times, then you got the new velocity is also going to be 0, and therefore the acceleration is 0 minus 0 over some new time, and we get the acceleration is equal to 0. So from this, we can say that the normal force, which is positive, so I'm going to put that as positive Fn, minus, remember it's technically adding, but it's adding a negative component of 49.0 newtons. So Fn minus 49.0 newtons is equal to 0. That tells us that the normal force is equal to 49.0 newtons. So I'm just going to write that as 1 because I'm going to make use of it later. And if you number your equations or in fact your results, that might be helpful so you can refer back to them and by a symbol. Okay. It's going to make more sense when we start solving the system of equations. Now I'm going to do the summation of the forces in the x direction equals mass times acceleration in the x direction, again for the 5 kilogram mass. In this case, we see that the only force we have acting in the x direction, oops, I haven't drawn the other one yet. The only force that we have drawn right now is just the tension, but remember this is a problem with friction. So I had actually left off a force, which would be in the negative direction, and that's the kinetic friction. So the summation of forces on the left-hand side is going to involve the tension and the friction force, and the tension is acting in the positive direction, so that'll be T, and then plus negative Fk. But Fk is mu k times the normal force, so I can write this as T. Oops, I should go back to green. I can write this as T minus, again, we really are adding, but we're adding a negative, so why write two signs? In this case, it's going to be 0.200. That's the coefficient of kinetic friction times the normal force, which is 49.00 newtons. And all of that is equal to 5.00 kilograms times the acceleration, which is the only acceleration that we're dealing with, so I don't need to subscript it 5 or y or x or anything like that. Now, I do have to compute what 49 times zero point 0.2 is. Obviously, the two, the fact that it's a decimal says it's 2/10. So I can make that 4.9 times 2, and then of course 4.9 times 2 is 9.8. So that gives us T minus 9.80 newtons, and actually that's I shouldn't underline that digit. It should be 9.800 newtons is equal to 5.00 kilograms times A, and that will be called equation 2. So that's the summation of forces in the x direction equals mass times acceleration in the x direction, and it gave us equation 2. Now I'm going to take the 2 kilogram mass, and that one really only has a x direction to deal with. We don't have a two-dimensional situation going on here. So in this case, I'm going to take the summation of the forces in the x direction equals mass times acceleration in the x direction. In that case, we see the 19.60 is acting in the positive direction, so that's 19.60 newtons. And then the t is acting in the negative direction, so I'm going to write minus t, and that's equal to 2.00 kilograms times a, and that's going to be equation 3. So we have two unknowns. We have the tension T and we have the acceleration A. We're only asked for the acceleration, but of course you would always want to be able to solve for the other one just in case. So I'm going to show you that either way. But the big thing here is one of the methods that you learned in hopefully high school algebra 1, but it might have been in pre-calculus algebra. But the main thing is when you're solving a system of equations, sometimes you'll have the one of the unknowns in one of the equations has a coefficient of like positive 3. And if the other one has a coefficient of negative 3, then a smart way to deal with that is add those two equations, because 3x plus negative 3x gives you 0, and you've already eliminated one of the unknowns. So that's what we're going to do here, because we see in equation 2 I have a positive t, in equation 3 I have a negative t. So if I add the left-hand side of equation 2 to the left-hand side of equation 3, the t's will cancel out. And then adding the right-hand side of equation 2 to the right-hand side of equation 3, the t's aren't going to cancel out there, but we're going to get basically two numbers, each of which are multiplied by a, so that I can have a common factor of a. And instead of just having a, I'm going to have a times parentheses 5 kilograms plus 2 kilograms, which is 7. So that's how I'm going to solve my system of equations. And I would write it like this. Let's say add 1 to, or excuse me, add 2 to 3. So there's my verbal cue where I can look back in my notes and say, oh, okay, I added equation 2 and 3. So that reminds me, yes, I've used equation 2. Yes, I've used equation 3. If I saw that I had already put in the normal force in equation 2, for instance, then that would also convince me that I'd also use that fact. So I can keep track of everything that I've used, because when you have, I'm sorry about the dogs, y'all. Because when you have multiple equations and multiple unknowns, the fundamental rule of algebra says if you have n equations and you have to have uh, if you have n unknowns, then you have to have n equations. You can't solve it if you have less equations than that. You've got to have the same number. Jesus H. Who's here, Brian? Okay. Sorry about that, everyone. All right. So, anyways, so when you're solving a system, let's say two equations, two unknowns, you got to make sure you use both equations, because algebraically you can make a careless mistake. And if you make that careless mistake, you might actually make another careless mistake and convince yourself that you've solved the system and get a right answer. But if you look back in your notes, you'd see that you didn't use both equations, and therefore you know your answer is wrong. So that's just good note keeping up with everything. So with this, I'm going to add equation 2 to equation 3. I'll go ahead and show you all the steps that I normally wouldn't show. So I'm going to say T minus 9.800 newtons plus, now I'm adding the equation 3's left-hand side. If I was subtracting or if I was multiplying equation 3 by a constant of some sort other than 1, it would be very important that I remember to distribute. So I'm going to put parentheses around the left-hand side of equation 3 just to remind you that that is good procedure. You should always do that, even when you're adding, but especially if you're subtracting or multiplying by something. So by putting it in parentheses, I know it's going to be 19.60 newtons minus T, and then the right hand side gives me 5.00 kilograms times A plus, again, parentheses, 2.00 kilograms times A, like that. So for the same reason that I added the parentheses before, I'm doing it on the right hand side too. Not really relevant here because it's just a coefficient of positive 1, so it's nothing going to happen by distributing. So I can now see that the negative t in here is going to cancel out with the positive t in here. And I can also see that I've got a 5 kilograms times A plus a 2 kilograms times A. That's going to give me 7 kilograms times A. And in fact, 19.6 minus 9.8 is going to give me 9.800 newtons for the left-hand side is equal to 7.00 kilograms times A for the right-hand side. Oh, good. Y'all can't hear it. I'm glad. I was afraid it's so loud here. I was really getting angry. So thank you guys. I appreciate that. Thank you for letting me know. All right. Now I solve for A, and I get A is equal to 9.800 newtons divided by 7.00 kilograms. Again, is a newton is a kilogram meter per second squared. So dividing out a kilogram is just going to leave us with meters per second per second. So if I divide 9.8 by 7, that gives me 1.400. So that gives me 1.400, and I obviously only had three sig figs. So that's 1.40 meters per second is equal to the acceleration A. Any questions on that? All right. So it's pretty straightforward. Now, just for to show you how this is done, once you've got that, then you can plug the A in equation 2 or equation 3, and that'll allow you to figure out the tension. So I'm going to do that now. And in fact, since equation 2 has the T with a positive sign already, then I'm going to use equation 2. So I'm going to say, and I'm going to write this in red because this is extra, plugging A equals 1.400 meters per second into equation 2, we're going to get the following. T minus 9.800 newtons is equal to 5.00 kilograms times 1.400 meters per second. That means T is going to be equal to, when I multiply 5 times 1, I get 5. When I multiply 5 times zero point 0.4, I get 2. So this would be 5 plus 2 is 7. So I'd get 7.00 newtons. And then I've got to pull the 9.8 to the other side, so that'll be plus 9.800 newtons. So finally, I can say that the tension should be 7 plus 9.8, which would be 16.80 newtons is the tension in the rope. And you can see that tension is about, it's about 17 newtons, whereas the weight of the actual 2 kilogram box is 19.6. If it was a full 19.6, then obviously the box wouldn't accelerate downward at all. So it makes some sense that it is a little bit smaller than 19.6. Anybody have any questions on that one? All right. So now we're going to move on to example 5, 6, and this is teaching you something else, which we sort of hit on that other video. Specifically, if you have an inclined plane, let's say like this, like here's your inclined plane, and you have this object on it, what makes that object slide down the inclined plane? Because you see the force is actually pointing straight down. Straight down does not point diagonally down to the right. So what does it? Well, we'll show you this with example 5, 6. So example 5, 6 says the skier. The skier in figure 5, 8 descends a 30-degree slope. If the coefficient of kinetic friction is 0.10, what is her acceleration when she is in contact with the snow? So we're given a very little amount of information here. I'm going to add an extra sig fig because I'm OCD like that. So I'm going to say the angle is 30.0 degrees, and I'm going to say the coefficient of kinetic friction mu sub k is equal to 0.100. So that makes it 3 sig figs as well. And what they want to know is A equals question mark. So the regular diagram would just be basically an inclined plane at 30 degrees. That's more like 45, but I think y'all get what I'm doing here. Here's the skis, and there's the skier skiing down. Okay. Now, it turns out when you're working with things on inclined planes, there's one example, and it's an example that comes in chapter 5, but there's one example where it's not necessarily best to tilt the axes to parallel to the inclined plane, but virtually every other instance is better to tilt the axes so that they're parallel to the inclined plane. So that's what I'm going to do here. So I'm going to make my free body diagram with the x-axis tilted downward, and sometimes we prefer to call that x prime because the x would normally be just the axis that's pointing vertically to, or excuse me, horizontally to the right, and the y prime would, or the y-axis would be the one pointing vertically. So we use x prime and y prime for it. Not really critical, but just know that's a normal thing that we do. We have the mass, of course, that's m, and they didn't give us it, so we're hoping that it's going to disappear. How you'll know that you didn't need it is if you get the equation that would give you, for instance, the acceleration, and if the mass can be canceled out of it because it happens to appear on both sides of the equation, then you know that the mass was irrelevant, and that's the key point here. So let's remember that. Now we have a force acting on the skier. The force that is due to something touching it is clearly the normal force due to the snow. So that points in the upward y direction. So that's going to be a positive component. So there's our normal force, and notice it's parallel to the y prime axis. Now that's all that's touching the girl. Obviously, there's wind touching her, but we're ignoring air resistance, so we can forget about that. That leaves us only to our action at a distance forces, which is the force of gravity. And the force of gravity is not parallel to one of the axes, so I'm just going to draw it blue. Actually, I meant to draw it blue, but I had the wrong color loaded. So I'm going to draw it blue, and that quantity is just W is equal to M times G, and we don't know M, so why bother doing more than multiplying? So I don't need to call that 9.8 times M. I'm just going to call it mg. All right, now the big trick on all this is we also, sorry, the snow is also applying a friction force. I almost forgot it again. That's two in a row. The friction force, since the person's sliding down the incline, the friction force tries to oppose that relative motion. Therefore, the friction force will point up the incline, and that's in the negative y direction. So I'm going to call that red vector the kinetic friction F sub k, which is a lot better just to write. What the hell? I'm gonna. My brother just made the most obnoxious coughing noise I've ever heard in my life. I'm like, I ain't never heard him cough that loud before. Anyways, the friction force is going to be just plain F, so it's mu k times the normal force, which we're going to figure out the same way we did before. We've got to do summation of forces in the y direction equals mass times acceleration in y direction. That's going to allow us to determine our normal force, and then we got to do the summation of forces in the x direction to determine the acceleration. So before we can do that, we still have this problem of this blue vector, and this is the one of the main points of B showing you or telling you to watch last time's video as well as this one, because a big part of this is you've got to know certain geometry, and the geometry that we need to know here I'm going to show you. Remember, the x-axis is supposed to be tilted as if it's perfectly parallel to the inclined slope of the ski slope. So that means that this angle between this x-axis and the horizontal is 30.0 degrees. Now, if you look at that, you'll realize, hey, wait a second, this line is vertical, this line's horizontal. That means this forms a right angle, and that means that this forms a right triangle. Because this forms a right triangle, then the sum of the angles inside of a triangle is always 180. In flat space, it's always 180. We've already accounted for 30 for this angle, and we've accounted for 90 for this angle. 30 plus 90 is 120, so that leaves an angle of 60 degrees up here. So this angle is 90 degrees minus 30 degrees, which is 60 degrees. So I'm going to go ahead and write up here that this is 60.0 degrees. Now, the other big thing is to realize that this slope axis and this perpendicular axis are actually at 90-degree angles to each other. So this too is a 90-degree angle. And that means the 60-degree angle and this angle are what we call complementary. Just like the 30 and the 60 were complementary because they're two angles of a right triangle that's not the 90-degree angle. So they have to add up to give you 90. Well, this angle and this angle has to add up to give you 90. We already have the 60 accounted for, so that means this angle up here is 30 degrees. So now we can make this into a right triangle of components for the W, where this is our right angle right here. This is our Y component of W, and this is our X prime component of W. This is our Y prime component of W, and this one's our X prime component of W. So now all I have to do is draw those components. Obviously, the Y one is going to be in the negative direction, so I'll draw it as red. So that's going to be the Y component. And then the X component, the X prime component, is going to be parallel to the positive direction. So that's going to be green. And from trigonometry, we can see that the sine of 30 degrees is equal to opposite over hypotenuse. So this side is given by sine, and this side is given by cosine. So we can go ahead and write, using the colors that they are, this side is going to be mg cosine 30 degrees, and this side is going to be mg sine 30.0 degrees. So that was a big part of this problem, and the problem that we did earlier with an inclined plane in the other video specifically is you working out the geometry, because you're going to have inclined planes a lot. You got to do this a lot. All right, now we can go ahead and focus on our summation of forces in the y prime direction. So the summation of forces in the y prime direction is equal to mass times acceleration in the y prime direction. But as you can see, this snow skier, if we're assuming she's not jumping and stuff like that, we expect her to move exactly parallel to the slope, so that her y coordinate, which is 0, her y prime coordinate, which is 0, is going to continue to stay 0, stay 0, stay 0. And again, we reach the conclusion that the acceleration in the y prime direction is equal to 0. Now all we have is to write out the positive force, which is the normal force, Fn, plus the downward force, which is the negative mg cosine 30. So I'm going to say minus mg cosine 30.0 degrees is equal to, that's it. That's all the forces that are acting vertically. So I set that equal to 0, and that tells us that the normal force is mg cosine 30.0 degrees. Of course, for an arbitrary angle theta, it would be mg cosine 30. If you watch, I believe it's episode 2 of season 1 of Big Bang Theory, you'll hear them trying to navigate a stairwell with a Swedish entertainment center, and they're both nerds and they're too weak to carry anything up the stairs. So they're using physics, and they said, okay, so we've got it on an inclined plane. Call the angle 30 degrees. We reduce the force by the sine of 30 degrees. Call it 1/2. That's what they're talking about here. So what we're going to find is that the force that's actually pulling it down the incline is going to be mg times the sine of 30. We'll see that by doing the summation of forces in the x prime direction. So the summation of the forces in the x prime direction equals mass times acceleration in the x prime direction. This one's going to give us the only acceleration, so we're just going to call it a instead of a sub x prime. The forces acting in the x direction are the mg sine 30, which is positive, so that's going to be mg sine 30.0 degrees, minus the friction force, which kinetic is just a straight formula, so that's going to be 0.100 times the normal force, which we just found was mg cosine 30.0 degrees. And all that's going to be equal to m times a. And this is where you see that there's a common factor of m everywhere. So I can divide the left-hand side by m, and that'll actually cancel out the m's on the left-hand side. But when you have an equation, whatever you do to one side, you got to do to the other. So when I divide the right-hand side by m, that also is going to make the m's cancel out. And lo and behold, I'm going to get a is equal to g times, now in this case, I've got sine 30, 30.0 degrees, minus 0.100 times the cosine of 30.0 degrees, and that's the actual acceleration. So we can go ahead and calculate that either in terms of g or just as a number. So obviously the sine of 30 is 1/2. The cosine of 30 is 0.866, and then times 0.1 would be 0.0866. So I'm going to take sine of 30, and I'm going to say minus 0.1 times cosine 30, and that's going to give me 0.4134, 0.4134, and that is no units whatsoever. So that is 0.4134 G, and of course we only had 3 sig figs, and that was more or less multiplying. Of course, what we had was a little bit of addition, so we got to pay closer attention to that. But now we can also multiply 0.4134 times 9.8, and that gives me 4.051. And that's meters per second every second is equal to the acceleration. And that's the acceleration we're supposed to get from this. Anybody have any questions on that? Thanks, Michael. All right, so now you've seen why an object actually slides down an incline. It turns out that when you have a vertical force like the weight pointing straight down, that breaks up into a component perpendicular to the axis or to the incline, and then another component parallel to the incline. That component parallel to the incline is what causes the object to slide down an incline. So hopefully we've learned that now. All right, now we're getting to the nastiest of the nasty of this chapter, more or less, and it's example 5-7. So let's work this one out. Oops. So example 5-7. It says a ramp, a pulley, and two boxes. A box of mass MA equals 10.0 kilograms rests on a surface inclined at theta equals 37 degrees to the horizontal. It is connected by a lightweight cord which passes over a massless frictionless pulley to a second mass of mass MB. Our second box of mass MB, which hangs freely as shown in figure 5.9. A, if the coefficient of static friction mu static is mu static equals 0.40, determine the range of values for mass MB will keep the system at rest. And then B, if the coefficient of kinetic friction is 0.30 and MB is actually 10 kilograms, determine the acceleration of the system. So I'm going to write down the values that we have there. So I'm going to do that first, but I want to write down those quantities. Hold on a second. So we have a mass MA is equal to 10.0 kilograms. It's okay, y'all. The students told me that they can't hear y'all, so it's actually a lot better than I thought. So y'all are cool. The dog's barking is probably a little bit much, but other than that, it's okay. Uh, the theta, they actually said 37 degrees, and that's code word for me. I recognize that immediately. They're talking about the 345 triangle. So I'm going to expand that to 3 sig figs, and in fact, it's going to be 36.9 degrees because it's supposed to be 36.87 is what it rounds to 4 sig figs, but I'm going to call the angle 36.9 degrees. MB is what we're looking for. So that's the question mark. The static coefficient of friction, mu sub s, is 0.400. Notice how I added an extra sig fig there. The coefficient of kinetic friction, mu sub k, is actually equal to 0.300, like that. And for part A, they wanted to know m sub b. And for part B, they want to know what the acceleration is. So B, if m sub b is equal to 10.0 kilograms, what is A, the acceleration? So let me draw the diagram, then I'll draw a free body diagram as well. So our diagram looks something like this. We've got a pulley attached to an inclined plane. We have a rope that's going over a pulley and then runs perfectly horizontal or perfectly parallel to the incline was what I was shooting for there. I don't say that I drew it very well, but that's supposed to be what it is. So this is the 10 kilogram mass. That's the 10 kilogram mass right there. And I couldn't have made that written any worse. So I'll just call this M sub A, make it a little better like that. Okay, and then in addition to that, I have the mass M sub B hanging. So that's the actual diagram that we're talking about. And this is the angle theta that I just pointed out. So as I warned you, whenever you have an inclined plane, it's almost always better to create a coordinate system that's inclined. So I'm going to go ahead and draw my coordinate system. And this time I'm going to choose up as the positive coordinate direction. At least in one case I will. And then perpendicular to that is this. So this is going to be my y prime axis. This is going to be my x prime axis. My mass is going to be a little point particle right at the origin. And that's the 10 kilogram mass. But this is just the inclined plane ones. And I'm going to draw it in this case. I'm going to draw it assuming, well, let me put it this way. We don't know right now whether the mass hanging on the other side is going to be big enough to cause it to go up the incline, or if it's going to be so small that it's going to allow it to go down the incline, or it might be just in that sweet spot where it doesn't allow it to move at all. What's going on there, though, is in each of those cases, the friction forces are acting different directions. If, for instance, if MA is being pulled up the incline, then the friction force is going to point down the incline. If MA is sliding down the incline, then the friction force is going to point up the incline. And if the mass MB is just the right size so that MA doesn't move, the friction force is just going to keep it from sliding down the incline and therefore points up. And it's just a kinetic friction, or excuse me, just a static friction instead of kinetic friction. So what we're going to do is consider the two scenarios. We're going to consider the scenario in which the mass MA gets pulled up the incline, and we're going to consider the same scenario except with the mass A being going down the incline. So we'll say MA goes up. Okay, so with that in mind, I have a force that isn't parallel to one of the axes, so I've got to draw that as just a plain color purple. And that's going to be 10 times 9.8, so that's 98.0 newtons pointing downward. And actually, I've got this too small to make it very useful, so I'm going to draw it over again. Okay, so this is MA goes up again. This angle right here is 36.9 degrees. And of course, that means this angle from the argument we just made is also 36.9 degrees. And that means I can break this weight up into, and by the way, 10 times 9.8 is 98. So I'm going to call this 98.0 newtons is the weight. But we can see that the y component, of course, is going to be negative, and the x component is also going to be negative because I chose x as positive pointing up the incline. So this one's going to be 98 times the sine of 36.9. That's this component right here is going to be 98 times the sine of 36.9. So 98 times sine 36.9 gives me 58.84. Oops. Newtons. And the other one will be 98 times the cosine of 36.9. So 98 times cosine 36.9 gives me, in this case, 78.37 newtons. And that's carrying one extra digit, as I said. So now, in addition to that, since we're saying it's going up, that means there's going to be a friction force acting downward, and that's our negative x direction. So I'm going to draw that here, and that's the friction force, specifically kinetic. And then we have a tension force because the rope is pulling it up the incline, and that one's going to be a positive force. So I'm going to draw that in green, and that is our tension T, like that. So this is all MA goes up. Now, in addition to that, we have to consider the same scenario except with MA going down. So I'm going to draw another free body diagram just like that one. I'm not going to change the direction of the axes, even though that would make my signs come out to be positive and a little more friendly, but I'm not going to do that. So here's my x prime axis again, and there's my y prime axis, and there's my little mass right here. And again, we're going to have a purple force acting straight down. That is 98.0 newtons. But luckily, we still have the same y component of weight, and we still have the same x component of weight. And this is still 36.9 degrees, and this is still 36.9 degrees, and that makes this 78.37 newtons, and that makes this 58.84 newtons. And now, in addition to that, we have a normal force acting upward, which I didn't draw in the other one, I just noticed. So there's our normal force. I got to draw that over here as well. So there's our normal force. And we still have a tension force pulling up the incline. But in this case, MA goes down. So with MA going down, that means the friction force is going to act up the incline, and therefore it's actually what we'd call a positive force. So there's my friction force right there. And I got the tension, I got the normal force, I got the weight. That seems like everything. Now, in addition to that, I still need the free body diagram for the hanging mass. I'm going to draw that over to the side. And remember, we're going to assume, like we did previously with the pulley, we're going to assume the pulley is frictionless and massless, so the tensions are the same in the two sides. Not only that, since we're considering up is going positive, we're going to see, say for the left hand side, down is positive, so that we have that nice little linkage where if the M sub A moves up 1 inch, then the M sub B moves down 1 inch in the same quote unquote direction. So that's our X prime direction. So here's the way I do that. There's my X prime axis. Here's my mass, M sub B. Then acting on it, of course, is the tension force, which is in the negative direction. Same tension force that we had before, but we also have the weight, which is MBG. Okay, so that's the same for both scenarios. It doesn't matter. Okay, now I'm going to take the summation of the forces in the y prime direction equals mass times acceleration in the y prime direction. And again, just like we said, the perpendicular direction, there's not going to be any changing of the y coordinate, so the acceleration in the y direction is going to be 0. And for that reason, I get F sub n, the normal force, minus the 78.37 newtons. That's all of the total y direction forces. All of that has to equal 0. Notice it's the same for the left diagram as it is for the right diagram. So it's the same either way. And that tells us that our normal force is going to be 78.37 newtons. I'll call that 1 just because I need that result. Now I'm going to do the summation of the forces in the x prime direction for MA going up. So for MA going up, we have in the x direction, we have only the positive t. So that's going to be t. Oops. That's going to be t. Actually, I'll write it a little bit further to the right so it's under that. T minus, now the friction, the kinetic friction would be the 0.400 times the normal force, which is 78.37. Oops. Newtons. That's the T minus the friction force. Now, in addition to that, we're also going to have the minus 58.84 newtons as well. All of that is going to be equal to 10.0 kilograms times A. So that is our expression. And in fact, there's different ways we could do this, but one thing we could, for instance, do is we could solve for instance, the tension force, and then realize if that tension force was fully the MB times G, then we could get an estimate of exactly what that force or what that acceleration would be, and we could actually use it to determine what M sub B is. So we'll take it from there. Let's go ahead and simplify this by doing the multiplication and the addition. So zero point 0.4 times 78.37 is going to be equal to, excuse me, zero point 0.4 times 78.37 gives me 31.35. So this is going to be T minus 31.35 newtons minus 58.84 newtons is equal to 10.0 kilograms times A, like that. And let's see what else. That's our friction force. Okay, so now I want to combine the friction force and the 58.84 newtons. So we're going to say 31.35 plus 58.84 gives me 90.19. So I'm going to say T minus 90.19 newtons is equal to 10.0 kilograms times A, like that. Uh, Now, what we've worked out here is basically the summation of forces in the x direction, and what we could do is go ahead and solve for the or for the tension uh, in the rope. And when we did that, we'd say T is equal to 90.19 newtons plus 10.0 kilograms times A, whatever that acceleration would be. But what we could do at this point is we could say, wait a second, let's assume that the acceleration is just zero, so that it's basically it's free to move. We've overcome the force of friction, the force of static friction specifically. And I did have that as point 0.4, right? Yeah, I did use that. Okay. I was just making sure I used the point 0.4, not the point 0.3. So I could do that and then assume the acceleration is zero, and that would be the smallest case. So we can say if t is equal to mbg and a was equal to zero, then mb is exactly the correct weight, mass really, at which static friction is overcome. In other words, uh, if I set that equal to that, that's the bare minimum for the bare minimum mass that could be hanging on the side that would make it move up the incline. And that's one of the numbers we're wanting. We want to know what's the minimum mass at which it makes it move up the incline and what's the maximum mass at which it doesn't allow it to move down the incline. So we've now done that. All we have to do is say T is equal to M sub B times G is equal to, since A is equal to zero, and that's because of this part right here. Oops, I wanted to show that in red. Because of that, we're going to say MBG is equal to just the 90.19 newtons. Therefore, we can see that MB is equal to 90.19 newtons divided by 9.80 meters per second per second. And lo and behold, we get 9.2 kilograms. So if it's 9.2 kilograms, it'll just start to go up the incline. Next, we're going to look for the case in which it just is enough to keep it from going down the incline. But we now have one of the limits, obviously at 9.2 kilograms. That's one of the results. Now what we got to figure out, as the question said, let me reread the question again, just so y'all know. If the coefficient of static friction is mu sub s equals zero point 0.4, determine what range of values of mass mb will keep the system at rest. So now I got to consider the case where ma goes down. And to do that, I'm going to say the summation of forces in the x direction. I'm going to do this in purple just to make it stand out from the other one. So the summation of the forces in the x prime direction equals mass times acceleration in the x prime direction. Now, in this case, we're going to take just the x components. We already got the normal force, all that stuff. But in this case, we've got the tension and the friction are both positive. So this is going to be T plus 0.400. That's, by the way, I'm taking some liberties here. I'm actually allowing the static friction to be the largest value possible because that's the critical value at which the mass becomes just enough. So I didn't mention that in the previous one, but hopefully y'all understood that's what I was doing. Just in case you didn't, I wanted to make sure you do now. So I'm saying the 0.40 times the 78.37 newtons. That is the T plus the F, and now I've got to say minus 58.84 newtons, and all that's equal to 10.0 kilograms times A. So in this case, we can simplify a little bit. Zero point 0.4 times 78.37, we already know what that is. So this is going to be T plus 31.35 newtons minus 58.84 newtons is equal to 10.0 kilograms times A. That's really the worst thing I've ever done. So I'm going to go ahead and write it down here. T plus 31.35 newtons minus 58.84 newtons is equal to 10.0 kilograms times A. So doing this again, in this case, what we need is T plus F uh, to just be small enough where the force of the 58.84 is equal to it. And that would cause an acceleration equal to zero. And therefore, we could set that equal to the tension in the other side, and that would give us our smallest mass. So just like I did before, I'm going to assume A is equal to zero. I'm going to say, let me write this in red. Again, let A go to zero and set T equal to MB times G. In doing that, we're now going to say, T is equal to 58.84 newtons minus 31.35 newtons. And that's all going to be equal to MB times G, so that MB is going to be equal to 58.84 minus 31.35 gives me 27.49 divided by 9.80 meters per second per second. And for that, I get 2.8 kilograms. And actually, that other one should have been to 3 sig figs as well. So that should have been 9.20 kilograms. So we now have two of our answers. We needed the maximum mass and the minimum mass. So the maximum mass is the 9.20 and the minimum mass is 2.80. So if the mass is between 2.8 and 9.2, then the mass on the incline is going to stay sitting still. But if the mass is bigger than 9.2, then it's going to accelerate up the plane. If the mass is smaller than 2.8, then the mass is going to slide down the incline. And what they asked specifically for part B was if the coefficient of friction is mu k equals zero point 0.3, meaning we've overcome the static friction and we're now into the kinetic friction realm, and mb is equal to 10 kilograms, determine the acceleration of the system. So now all we got to do to finish this up is we're going to actually take the other equation and solve the system, but for the case where it goes up the incline, which is the first case, MA goes up. So I'm going to try to use all that information. That means I'm going to steal this. Actually, let me steal this one instead because this is a little better looking. So I'll copy that. Now I'll pull it over to the next side. And now I'm going to do paste. So that's the equation that we actually have for going up the incline. Now the other equation we have is going to be the summation of the forces in the x prime direction equals mass times acceleration in the x prime direction. And that's purely for this diagram right here. With that diagram, what we have is MBG, which in this case is going to be 10 kilograms times G, minus T is equal to MBA. So I'm going to say, uh, oops, better write it in letters, 10.0 kilograms times 9.80 meters per second minus T is equal to 10.0 kilograms times A. So that's the equation, which I'm going to call this one equation 2, say, and call this one equation 3. That's my two equations, the one for the hanging mass on the right and the one for the mass on the incline in the blue on the left. So just like we did before, I see a common T. One's got a negative coefficient and the other one's got a positive one coefficient. So I'm going to add the two. So uh, add equations 2 and 3. And getting that gives me T minus 31.35 plus 58.84 gives me 90.19. So that's going to be T minus 90.19 newtons is equal to, or excuse me, that's just the left-hand side of equation 2. Now I'm going to add to that the left-hand side of equation 3. So that's going to be 98.00 newtons minus T. And then the left-hand side and the right-hand side add to give me 10 kilograms A plus 10 kilograms A, which is 20.0 kilograms times A. Notice the T's cancel out, and I get 98 minus 90.19, which gives me 78. Oops, wrong color. Which gives me 78.10 newtons. Wait a second, that should be 7 point. Yeah, that should be 7.810. Sorry about that. So 7.810 newtons is equal to 20.0 kilograms times A. So A is equal to 0.3905 meters per second every second. So the acceleration for those, when we actually do use the 10 kilogram mass, we end up getting 0.39, and I don't know where I got that. What happened? The masses were both still 10, right? I seem to have dropped something. This looks like it's twice as big as it should be. And I don't know where I got the extra 2. Let's see, 98 minus 90.19. Anybody find any mistakes that I made so far? So like that. Just trying to look here, make sure I took the right part. Minus 31, be 80, 88, 90. 90.19, T minus 91.19. That looks right. And 10 kilograms times 9.8 would be 98. That's right. And there's T, so that looks right. No one find any errors with this? Well, let's look. I want to look back at the original diagram just in terms of the mass sitting right here on the incline. We had uh, up the incline was the positive direction. Oops, so that should have been green. So that would be the tension pointing up the incline. We also had the force mg sine theta pointing down. Since it was going up, we also had then that should have been a red force. So this should have been mg sine theta. But in addition to that, there should have been the friction force, which is mu static in this case times the, that's what it was. The mu static. I think I used the coefficient of friction. Yep, that's exactly what I used the coefficient of friction from the previous one. So the 31.35 newtons was the friction force. That's not right. So that's why it came up uh, too large of a force. So when I copied this formula, that was a good idea, but it was also a stupid idea because notice it used the point 0.4, and in fact it's supposed to use the zero point 0.3 that we wanted for part B. So that's what went wrong. I can fix that now. Let's see. I'm going to go ahead and erase all this. Well, that part I could have left. I'll put that back in a second. But let's kill this. Let's make my eraser dot a little bigger. Okay, and what we have wrong here is the 31.35. This 9.80 times 10.0 kilograms, that's fine. So we got 98.00 newtons minus T is equal to 10.0 kilograms times A. That's going to be what I call equation 3. Now, the mu static would be zero point 0.3 times the normal force, which is 78.37. So when I do those two, I'm going to get 23.51. So it's T minus 23.51 newtons. And this is 0.300 times 78.37. And I think I might have even done that wrong. Zero point 0.3 times 78.3. Is it 37 or 38? Yeah, it's supposed to be 37. Same answer, 23.51. So yeah, that's okay. All right, now I'm going to add 2 and 3. Obviously, 23.51 plus 58.84. So 23.51 and 58.84. That gives me T minus 82.35 newtons is equal to 10.0 kilograms times A. That's my equation 2 now. So now when I add the two, I'm going to get T minus 82.35 newtons plus 98.00 newtons minus T. And remember, when we add the right-hand side, we get 10 kilograms times A plus 10 kilograms times A, which gives us 20 kilograms times A. So now I can say 98 minus 82.35 gives me 15.65 newtons is equal to 20.0 kilograms times A. So if I divide this by 20, that gives me A is equal to 0.7825 meters per second, with obviously a bunch of extra digits. But that's it. That's the acceleration due to that. Sorry about that little boo boo there. Glad we were able to find it, but at the same time, I hate that I made that mistake. But that makes a big difference, obviously, if you're using point 0.3 instead of point 0.4. Anybody have any questions on that? So the way Nathan asked about the t being negative, remember basically you decide what the t is when you choose the coordinate system direction. So you can see with the two diagrams, the t is going up the incline, which is the positive x and the positive x. But on this side, the t is in the negative x direction, and that's because we wanted the motion of 1 inch up the incline to correlate exactly with a motion in the positive direction of the hanging mass. So I had to point the x-axis pointing down for the hanging mass so that it would be aligned with the motion going up. Otherwise, I'd have to make another equation to relate the acceleration of the hanging mass to the acceleration of the mass on the incline, and it'd be something stupid like the acceleration of the hanging mass is equal to the negative of the acceleration of the other mass, something goofy like that, and just not worthwhile. So by doing that, that ended up giving us the t minus for these two. So these two diagrams gave us t minus here, and also t minus here. The main thing is the fact that the t was positive. The minus was the 58.84 here, but the t was positive here and the t was positive here, and that's because it was these diagrams. However, when I did this diagram, this direction is positive, so it would be mbg minus t, which is where I got mbg minus t there. Does that make sense, Nathan? That's a good question, but that's part of what I was saying earlier. Right now, you might not necessarily understand why the tension is done the way it's done. So, what I suggest you do is just remember that we're always going to have, when we have two free body diagrams for two separate objects, and they're both acting on by the same tension. In one diagram, the tension is going to point one way, in the other diagram, it's going to point the other way. So, you're always going to have one being positive and one being negative. Uh, Always expect that, and as time goes by, you'll either grow comfortable with it just because it always gives you the right answer, or you ultimately think about it enough and come up with an idea of understanding why. You can sort of think of it as like a Newton's third law sort of scenario, because it is sort of the same force, but it's acting in the opposite direction. So, in that sense, it really is an action reaction pair sort of thing, because the tension is on one mass when in the other case it's on a different mass. So, in that sense, that's why I said it sort of acts like the Newton's third law. All right, so that was the last of the nasty friction forces. What I want to show you next is a neat little thing that you can do. I did this on my video for Thursday night, so if y'all need to see it again, you can look there. But I'm going to do a quick and dirty derivation of what we call centripetal acceleration. So, and I say quick and dirty, it's actually quick and quite clean. But what I'm going to introduce you to is a little bit of vector calculus, because I can, right? So we use X to indicate the position on the X axis. We use Y to indicate it on the Y axis. We use Z to indicate it on the Z axis. But if we want a position in space, some books will actually use the X vector to represent the position. No one uses the Y. I've never seen anybody use the Y vector to represent it, but some people use the X. I'm going to use the R vector, which is what most authors do. So I'm going to say we can imagine the position of a specific object as being given by the R vector. Okay. Now, this R vector is a vector valued function. So it's actually a function of some variable that when you put in the variable, out pops a vector. So a vector, remember, has magnitude and direction. So what I'm going to say is imagine we have a vector valued function r of t, and that means its argument, it's a function of t time. Okay. Now it is a vector, so that means it has to have an x component, a y component, maybe even a z component. And actually, it doesn't have to have all two or even three. It could just have one and it'd still be a vector. But what I'm going to define the x component as is r times the cosine of, and this is kind of weird, but I'm going to write 2 pi over capital T times lowercase t, and then I'm going to put a I hat next to it, and that tells you that this whole quantity, r times the cosine of 2 pi over t times t, is the x component. And now I'm going to make another component, the y component, and that's going to be r times the sine of 2 pi over t times t, and therefore it points in the y direction. Notice I don't have a z component. We don't need a z component. Now, if you were to take time to actually graph this function as a function of time, this vector valued function as a function of time, then the results would look like this. Here's my x-axis. Here's my y-axis. And if you consider, what you could do is make a data table, if you will. So let's say t is one column of the data, and then r cosine 2 pi over t times t is x. That's one column, and r sine 2 pi over t times t is another column, and of course that one would be y. And we're going to take t equals 0 seconds, and in fact, to be, oops, I forgot how big I made my eraser. To make this consistent with good practices in the lab setting, I'm going to say t in seconds. Now, if you apply t equals 0, you obviously get just plain r for this one, and you get just plain 0 for this one. But it gets a little bit more complicated from there. I'm next going to use t over 4. So my next number would be capital T divided by 4. And when I put t over 4 in there, you can see that the t is going to cancel out with the t in the bottom and end up getting 2 pi over 4, which is pi over 2, which is, of course, 90 degrees. And the cosine of 90 degrees is 0, and the sine of 90 degrees is 1, so this one just becomes r. If you continue on like this, you can then do t over 2, and in that case, you're going to get negative r, and you're going to get 0, and then you can say 3t over 4, and in that case, you're going to get 0, and you're going to get negative r for the y. And then finally, you could say t total, which is 4t over t over 4 if you wanted. In that case, you're going to get r and 0 again. So what we've learned is, if we assume, for instance, that r is 3 little squares, then right here is going to be the first one, second one, third one, fourth one. So that's the r of t equal t, or excuse me, of t equals 0, 0. This is the r of t equals t over 4. This is the r for t equals t over 2. And this is the t for t equals 3t over 4. And this is also the t for t equals capital T. So what's actually happened here is we've managed to make a vector function that actually gives us
the trajectory of an object going in a circle. And in fact, you don't necessarily know this yet, but it's specifically an object going at a constant speed in a circle. Because lo and behold, check this out. Remember, v is equal to dx dt. Well, in 3 dimensions, that becomes v vector is equal to dr dt. So if I try to take the derivative of this, remember it's only a function of t. So that means the capital R, the 2 pi, and the capital T are all just constants. So when I take the derivative of r cosine 2 pi over tt, in fact, I'm going to call this quantity 2 pi over t. I'm just going to call it omega because it turns out it is going to be omega, but it's a lot easier to write omega than it is to write 2 pi over t. So let's just pretend that's r cosine omega t I hat plus r sine omega t. And we can always put back the 2 pi over t at any time we want. But in so doing, when I take the derivative of cosine, I get negative sine. So this becomes negative. And then don't forget, I have to use the chain rule. So I've taken the derivative of cosine with respect to its argument. Now I got to take the derivative of the argument of cosine with respect to time, which gives me just the omega. So it's going to be negative omega r sine omega t I hat plus, now I'm going to erase some of this table so we can make it a little clearer. And you can actually fill it out, even cut all those times in half and start with t over 8 and then 3t over 8 and so on. You'll get a little better fix of it. But that's the first component. Now, the second component, the derivative of sine is equal to cosine. So this one's going to be plus omega r cosine omega t j hat, like that. Okay. So now that's our velocity as a function of time. If you look at that and you tried to plot it, what you'd find out is this velocity is exactly perpendicular to the r vector. So that's the v at t equals 0. And I'm trying to draw them about the same length in each time. So this is the velocity at t equals t over 4. This is the velocity at t equals t over 2. This is the velocity at t equals 3t over 4, and so on and so forth. So you can see not only is it a circle, it's a circle in which we're going around it in a counterclockwise direction. And we can go further and calculate the magnitude of the velocity. The magnitude of the velocity, remember the Pythagorean theorem is all we need here. So this is going to be the square root of omega squared r squared sine squared omega t plus omega squared r squared cosine squared omega t. All of that square root. Notice you've got a common factor of omega squared r squared. And if I factored that out, it would be the square root of omega squared r squared times the square root of sine squared plus cosine squared with omega t, of course. But this is just 1. So the velocity actually has a magnitude of just r times omega. So v equals r omega is the magnitude of the velocity vector. So we see it's a constant because r is a constant and omega is a constant. It must be a constant. Now, I will tell you that omega is equal to 2 pi over t, but it's also 2 pi times f because f is 1 over the period, or period is 1 over the frequency. So those are the extra equations that you need to relate omega, f, and t. F is the frequency, and it's something we would measure in hertz or cycles per second. T is the period. That's the time it takes to make one complete cycle, and that would normally be measured in seconds. So you can see F and T should be reciprocal, at least by the units, because cycles per second, if you flip that over, that just becomes seconds per cycle, which a cycle is not really a unit, so you just call it a second. Now we can also take the acceleration, and that's kind of interesting. the acceleration is equal to dv over dt. So I have the velocity vector. We just calculated that. The acceleration would be taking the derivative of that. So if I take the derivative of negative omega r times sine omega t, the derivative of sine is cosine. So I'm going to get negative r omega squared. Notice I wrote it in a different order this time because I find it easier and more comforting to have the r before the omega. I don't know why. It's just what I do. So that's why I have that. And of course, when you take the chain rule, you've got to get another omega. So that's why it's omega squared. But the sine becomes cosine omega t, and then all that times I hat. Similarly, when I take the derivative of cosine, now I get the negative of sine, and I still get that other omega too. So this is going to be minus r omega squared, and this time it's times the sine of omega t, and that's the j hat. So that is the acceleration vector. And if you look at that, that is really just, notice, negative omega squared times r of t. Because of that, that tells you that the direction of this acceleration vector is exactly the direction of the r vector. So in this case, the acceleration is going to be there. In this case, the acceleration is going to be there. And here, oops, and here. So that's the acceleration. And in fact, if you wanted to take the magnitude of it, you can already see that the magnitude of RT is only going to be omega. So that also tells us that the A is equal to, in fact, omega squared R, like that. And if you wanted to, you might call this omega squared R squared over R, and then you'd see that that is V squared over R, and that's the big thing. That's what we were shooting for, is a quantity representing the centripetal acceleration. What acceleration is required to make something travel in a circular path? So, centripetal acceleration. Notice I'm writing centripetal, P-E-T-A-L. That means center seeking. Centrifugal means center fleeing. And that's actually, there's no such thing as a centrifugal force. Well, we'll say that because that's a common misunderstanding of physics, but it's something that we use in everyday life. So it's very normal to hear people say it. But in reality, there's no such thing as a centrifugal force. There's only Newton's first law of motion, which says that an object trying to go straight, or an object trying to move in general, is going to tend to go straight without changing its direction or its speed. And because you're trying to make it go in a circle, it has to have some kind of force that makes it center seeking, that makes it go in that circle. If without that, you would get slung sort of to the outside, but in reality, you're just using obeying Newton's first law of motion and going straight ahead at whatever point that force stopped existing. So the centripetal acceleration is a sub c, and that's v squared over r, and that points to center of circular path. Okay, we saw that from this derivation. Basically, we learned that the acceleration vector always points towards the center of the circle, and we found that its magnitude was omega squared times r, which worked out to be the same thing as v squared over r. V squared over r is the way I normally use it, but we could also use the omega squared r. That's fine as well. You just have to remember all those other linkages where omega is equal to 2 pi f where omega is equal to the angular frequency, and that would be measured in radians per second. But it's also called, let me erase this, it's also called the angular velocity. So that's another phrase that we use to represent omega, but it's generally measured in radians per second. And one of the formulas for it is really just a conversion from radians per second to cycles per second. And that's given by this omega equals 2 pi f, where f is called the frequency. And that frequency, of course, is measured in cycles per second, which you might see some old government manuals, they'll say CPS, but in reality, the modern version of it should be the Hertz. That's capital H, lowercase z, named after Heinrich Hertz, who you'll learn about in the 242 course. But frequency is the number of cycles per second. And then there's another quantity, T, which equals the period, or excuse me, period of rotation, R of revolution, R of oscillation. See, all of those things are things that repeat themselves. When we're talking about the period of rotation, that means the time required for it to go from that initial state to the same state it was. That is the period of rotation. If you're talking about an object orbiting another object, then it's the period of revolution, and it's the time required for, say, this particular planet to orbit this sun and go and end up right back where it started. That's one period of revolution. If it's a period of oscillation, then it's like it goes like this and then back to where it started from. That is one period. That's another period. That's another period. So that's where those quantities come from. And because of these relationships, we know that the frequency is equal to 1 over the period, or the period is equal to 1 over the frequency. And like I said, this can be seen as conversion from cycles per second to radians per second. Because remember, a complete revolution is 2 pi radians, and therefore a complete cycle is 2 pi radians. So really, we're just multiplying the cycles times 2 pi to get radians per second instead of cycles per second. Anybody have any questions on that? All right, your book does an entirely different derivation of the centripetal acceleration. I think mine's a little easier. I mean, obviously, you wouldn't necessarily come up with this on your own because you might not have ever encountered vector valued functions or vectors in this sort of way. But the math is so trivial to do, why not treat it that way? And you can automatically get these wonderful results that show you that the velocity linear velocity that we recognize in meters per second is just the radius of the circle that you're going in times the angular velocity. So the r times omega gives you the velocity in meters per second, where omega would be in radians per second and r is in meters. And similarly, you even have a formula for the acceleration. Another result of that, by the way, could have been a equals r times omega. That would have been another result as well that we'll learn later. But either way, that is a derivation. And just to give you an idea, let's look at example 5.8 real quick. And this is probably going to be the last example we can work before class is over. So example 5.8 says a 150-gram ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.600 meters. as in figure 510 or 512, the ball makes 2.00 revolutions, excuse me, in a second. What is the centripetal acceleration? So I have the mass is equal to 0.150 kilograms. They gave it to me as 150 grams, but obviously kilograms is what we're supposed to use, so I went ahead and converted it. The horizontal circle has a radius equal to 0.600 meters, and the ball makes 2.00 revolutions per second. Can anybody think which one of these symbols we should use for that 2.00 revolutions per second? Is this omega? Is this T? Is this R? Is it F? Anybody? Anybody? So since it says 2.00 revolutions per second, a revolution is the same thing as a cycle. So it turns out that this is F. So what they're telling us is F is equal to, and actually I can just put it to the side here, 2.00 revolutions per second, which equals 2.00 hertz. Okay, cycle and revolution mean pretty much the same thing. You can just assume they're the same thing. So what we're asked here is what is the centripetal acceleration? A sub c equals question mark. Solution, we know a sub c is either equal to omega squared r, or it's v squared over r. Either one of those is fine. We know since the object's going in a circle, and obviously, the average velocity is the whole velocity, because what we learned is that when an object's going in a circle like this on its own, then its velocity is going to naturally be a constant. If you actually speed it up, that's going to make part of the circle become an ellipse as opposed to a circle. So that's sort of the feedback loop. If you actually try to accelerate, that's going to make it harder to make that turn unless you change the centripetal force. Therefore, the radius is going to change. Therefore, you've got part of the circle is going to be a ellipse of a bigger size than the circle, and part of it's going to be a circle. So in this case, we can say V is equal to the distance traveled divided by the time taken. That's the average velocity, but like I said, we learned that in circular motion, that velocity is a constant. So the distance traveled when an object goes around the circle is called the circumference, and that is, of course, 2 pi times the radius. And actually, I already called it big R, so I'll put a big R up there instead of a lowercase. And then the time required for it to complete one revolution is technically called the period, T. So the velocity is actually 2 pi R over T. Now, the other thing to remember is that F is equal to 1 over T. So we can go ahead and make this 2 pi times R times F, and that will be the actual velocity. Putting all this in, I get 2 times pi times 0.600 meters times 2.00 hertz gives me 2 times 3.14159 times zero point 0.6 times 2 gives me 7.540 meters per second. Remember, our hertz is a cycle per second, so the second and the bottom's coming from the hertz, and the meters coming from the radius. So I now have the velocity of 7.540 meters per second. I only had 3 sig figs, so that zero is not a significant figure. Now, with that, I can say that the centripetal acceleration, a sub c, is v squared over r. So I'm going to take that 7.540 meters per second, and I'm going to square that and try to make sure I remember that, because the other night when I was doing this example, I wrote it and I said it, but I didn't square it. So do that, and then I'm going to divide it by 0.600 meters. You can see that when I square the 7.540 0.40 meters per second. That's going to give me some number of meters squared per second squared, and then I'm going to divide it by a meter, and that's going to give it just make it just become meters per second per second. So when I squared that, I got 56.85 meters squared per second squared divided by 0.600 meters. That's one extra digit there, divided by zero point 0.6, and that gives me 94.75 meters per second is equal to the centripetal acceleration, and that's the answer we're shooting for.
Anybody have any questions on that?
All right. Well, that's it. That's the last problem we want to do. I want to remind everybody tomorrow at 8 a.m. I will not be doing my lab. I'm going to get it done sometime tomorrow. I'm taking a friend to the hospital, so I won't be able to make that. But I will do it sometime either tonight or tomorrow. It'll be posted tomorrow on my YouTube channel. So please subscribe long enough to at least get a notification when that's posted. But that'll be for your lab tomorrow. The other thing is, remember, I moved the online test dates, and I think you might even have an online test due like tonight. So make sure y'all get that done if you haven't already. You're free to go. You're also should chat me your first and last names just so I know who was here. Again, not taking off any points or anything for people missing. It's okay. But thank you and have a good night. I'll wait for the last person to leave in case anybody has any questions. Thanks, Nathan. You have a question, Sam? All right, I think Sam might have left. So y'all have a good one, everybody. Bye bye.